Hello, welcome to another module in this massive open online course. Alright, so let us continue doing examples to illustrate the various principles of signals and systems, and particularly with respect to the properties and classification of signals and systems. Let me just correct a minor typographical error, that is m should be equal to 24, I think, as we had. So, this is periodic and the fundamental period is m equals 24, that was for the previous problem. And now today let us continue our discussion of various other examples for signals and systems, okay, based on the concepts that we have covered so far. I think you will remember that is with respect to, I think, the basic properties and classification. Various properties and classification of signals and systems. So, let us now consider the concept of an energy signal. So, let us consider a discrete time signal, right, dt for discrete time signal, that is convenient. So, this is a discrete time signal x n equals alpha n u n. Okay. Now, the question is this an energy signal? If so, what is this energy? If so, is this an energy signal? If so, what is its energy? Now, we have seen that the energy of a discrete time signal, okay, the energy of a discrete time signal. So, the question is alpha n into u n. Now, mind you, u n is the unit step function, which is equal to 1 if n is greater than or equal to 0 and equal to 0 otherwise. Okay. So, this is basically equal to 1 for n greater than or equal to 0, 0 for n less than 0, implies basically x n equals alpha to the power of n for n greater than or equal to 0, 0 for n less than 0. The energy of a discrete time signal is summation n equal to minus infinity to infinity magnitude x n square, which is summation n equal to minus infinity to infinity alpha to the power of n whole square, which is summation n equals minus infinity to infinity alpha to the power of 2n, which is basically 1 plus alpha square plus alpha to the power of 4 plus alpha power 6 plus so on. And recall that this is basically an infinite geometric progression, okay, with the ratio or the constant with the incremental factor of the geometric progression given as alpha square. Okay. So, this is an infinite geometric progression, correct, and therefore, the sum equals, well, sum equals 1 over 1 minus alpha square if magnitude of alpha is less than 1, that is important, okay, and this is equal to infinity, or the diverges if magnitude of alpha greater than or equal to 1. Okay. So, implies this is an energy signal equals n, or alpha to the power of n un, remember that is equally important. Okay. This is an energy signal if n, if magnitude alpha is less than 1, and in that case the energy is equal to 1 over 1 minus alpha 1 over 1 minus alpha square. Okay. So, this is an energy signal only if magnitude alpha is strictly less than 1, and in that case its energy is 1 over 1 minus alpha square. Otherwise, it is not an energy signal, its energy diverges. Okay. It means it does not have a finite energy. Okay. Energy is infinite. Okay. All right. Let us now come to another problem. And the problem is to evaluate the function delta A t. We know what is delta t. Remember, delta t is defined such that x of t, delta t for any function is equal to x of t evaluated at, this is equal to x of t evaluated at t equal to 0, this is equal to x of 0. Now, similarly, let us look at integral minus infinity to infinity for any function x of t times delta A t times dt. Now, obviously, this, if you look at this, I can substitute A t equals tau, which means dt equals d tau by A. For simplicity, let us also consider A greater than 0. You can also clearly evaluate what happens when A is less than 0. For A is greater than 0, we are considering a strictly positive A. This becomes, this integral therefore becomes integral minus infinity to infinity, t is equal to tau divided by A, delta A t is delta tau d tau divided by A. The limits still remain minus infinity to infinity, because dividing infinity by a positive constant A still gives infinity, same with minus infinity. So, the limits become minus infinity by A to, because tau is A times t, so limits become minus infinity times A to infinity times A, which are again basically minus infinity to infinity. So, limits remain unchanged, integral becomes minus infinity to infinity x of tau divided by A, tau over A, delta tau d tau over A, okay, which is now very simple. If you look at this, this is 1 over A x of tau over A delta tau d tau, which is 1 over A x of tau over A, now evaluated at tau equal to 0, which is equal to 1 over A x of 0. But recall that 1 over a x of 0, this is also equal to simply, well, this is also equal to simply integral minus infinity to infinity, well, x of t delta t over a, or 1 over a times delta t times dt. This is equal to your basically, this is basically equal to your minus infinity to infinity, well, x of t d of t or delta of a t holds for all x of t. This equality holds for, imagine this is for any arbitrary x of t. This implies, this only implies that this quantity must be equal to this quantity. This implies delta a t equals 1 over 1 over delta tau for any a greater than 0. So, that is basically your solution. So, delta a t equals 1 over a delta tau for any a greater than 0. Okay, so this holds for any a greater than 0, and therefore this implies that, naturally this implies that infinity minus infinity to infinity delta a t dt is equal to minus 1 over infinity 1 over a delta t dt equals basically 1 over a for a greater than 0. Okay, so that can be immediately shown. Okay, so delta a t if a is greater than 0 is simply 1 over a delta of t, that is the impulse function. Okay, with delta t is the impulse function. Okay, all right. Let us proceed on to the next example, which is even more interesting. Let us look at just writing this as problems, because I am not numbering them. I am just going to write this as problem to indicate that this is a fresh problem. So, we want to evaluate integral phi t delta prime t, where phi t is any function such that, let us consider phi t is any function such that phi of infinity, or basically limit t tends to infinity, phi of t equals phi of minus infinity equals 0, or in general this can be any constant, that is phi of t does not blow up to infinity or does not increase to either infinity or minus infinity as t tends to either infinity or minus infinity. Okay. Now, if you look at this, what I can do here is I can evaluate this by parts. So, what I will have integral phi of t delta prime t dt, this is equal to, well, integrating by parts, this is equal to, well, integrate delta t for delta prime t. So, that gives me phi of t delta of t between the limits minus infinity to infinity minus integral minus infinity to infinity, differentiate phi prime of t dt, phi prime of t, that is derivative of phi of t into delta t dt. Now this is equal to, well, delta t at t equal to infinity is 0, we have assumed phi of infinity is 0. So this is phi of t delta t evaluated at infinity is 0. Similarly, phi of t delta t evaluated at minus infinity equal to 0. So this quantity is basically equal to 0 minus, of course, minus infinity to infinity phi prime of t delta t dt. We know this quantity is nothing but phi prime of t evaluated at t equal to 0. So this is minus phi prime of 0, that is basically d phi by dt evaluated at t equal to 0. That is your answer, that is integral phi prime of phi of t delta prime t dt, that is minus phi prime of 0. Okay, so basically that is the solution to the problem. Okay, that is integral minus infinity to infinity phi of t delta prime t dt. Let us now look at some examples related to the properties of systems and classification of systems. Okay, the properties and classification of systems. So we will now look at examples related to properties. So far we have looked at systems. So now look at properties and classification. Let us now look at properties and classification of systems. Okay, so consider the so let us start with again yet another problem. Let us consider a simple problem. Consider the RL circuit below. This is a current source, okay, connected in parallel with a resistance and inductance. So this is, let us say, the current is the input, okay. Let us say the current through the inductor, this is the output, this is the output, this is the input x of t, this is your this is your current through the resistor, okay. This is the current through the resistor, this is an RL circuit. So we want to find an input output relation find input output relation for RL circuit below, for this RL circuit. Find the input output relation for RL circuit above. So I have, well, firstly you can observe that by Kirchhoff's current law you have I of t, that is the current of the source I of t is the current in the resistance plus the current in the inductance. Okay, so that is simply by KCL, the Kirchhoff's current law. Okay, so I can write IRT is, or I of t, I am sorry, apologize, I of t equals I of RT plus I of L of t. Now you can clearly see, if this voltage, we denote the voltage of the circuit by V of t, by Ohm's law IR of t equals V of t, I equals V by R. So, IR of t, the current through the resistance is simply the voltage divided by resistance, plus IL of t, okay, this is the simply the current through the inductor. Now, observe by the property. So, this is simply by the Ohm's law, this is simply by follows from Ohm's law, okay, that should be. Now, observe from property of inductor, we have V of t, voltage across inductor is L d IL by dt, which means I can write this equation as IL of t equals L by R d, or I of t, sorry, not IL of t, I of t equals L by R d ILT by dt plus IL of t, that is the current through the inductor, and we know this I of t, this is equal to x of t. So, I finally have x of t equals L by R d of, now IL of t is y of t, that is output. So, this is dy t divided by dyt with respect to d of t, that the derivative is, that is the so L by R dyt over dt, dyt over dyt dt plus y of t, and this is basically your input output relation, or basically writing it as, you can write it as L by R dyt dt plus y of t equals x of t, okay. This is the input output relation, which you can observe here is expressed as a differential equation, which is something very interesting. This is an input output relation that is expressed as a differential equation, input output relation expressed this is an input output relation expressed as a differential equation, and we will see in future how to solve this input output relation to explicitly derive an expression for the output, or explicitly derive an expression for the transfer function of the output in terms of the input. There are various ways to solve this, alright. So, right now this is represented, this input output relation between the input xt and the output with yt is represented as a differential equation in the time domain, which is a very valid, way to represent an input output relation, and it can be in fact seen that this is a linear system. In fact, it can be seen that this, you can verify that this is a linear system, this is a time invariant system. In fact, it satisfies all the properties of an LTI system, okay, all right. So, we will start. So, for this example, I think, this gives the input output relation, this describes the input output relation, okay. Let us continue with our problems. So, let us look at another interesting problem. This is a system which is termed as a modulator, and which is another very important operation, or another very important system in a communication system. T of xt equals x of t, let's put it this way, equals T of xt equals x of t cosine cosine 2 pi f c of t. So, this is your t of x t, which is the output, which is y of t equals x t cosine 2 pi f c t. This operation is known as modulation, and this frequency f c, this is known as the carrier frequency. Okay. This is known as the carrier frequency, and in fact this is a very important property, is a very important operation in a communication system. This is the very important system, or you can call it as a subsystem in a larger communication system. In fact, modulation, the process of modulating the signal, that is basically modulating it by a certain carrier, forms a very integral component, or forms a key aspect of any communication system. For instance, if we look at any modern cellular communication system, for instance, a system such as GSM has carrier frequencies around 800 to 900 megahertz. Modern 4G wireless systems, for instance, have carrier frequencies around the gigahertz, that is 2.1 to 2.3 gigahertz range. Even broadcast systems such as FM systems have carrier frequencies around 90 megahertz, correct? 90 megahertz to 100 megahertz. Amplitude modulation systems have basically frequencies in the range of carrier frequencies in the range of kilohertz and so on. Okay. So, this is modulation, that is modulating it by a different frequency, carrier frequency, so that it can be transmitted in a certain frequency band, so that the signal can be transmitted in a certain frequency band specifically allocated for that kind of communication, for instance as TV broadcast or AM radio or FM radio or 2G communication, 3G communication, 4G communication. This forms an integral part of any wireless communication system, be it a personal communication system such as your cellular telephony, or be it a broadcast, a broadcast communication system such as your radio or TV broadcast system. All right. So, this is a very important class of subsystems, that is because the modulation specifically, it is a system by itself, but it forms a subsystem in a larger system, that is a communication system. So, understanding this, its various properties is essential, and that is what its property, or that is what this problem aims to look at. So, we want to see, is this an LTI system? What we aim to examine is this modulation, is this an LTI system? This modulation system, is this an LTI system? All right. So, that is what we want to explore in this problem. All right. So, we have solved several problems in this module. So, we will stop here and continue looking at some other problems in the subsequent modules. Thank you very much.